Pluto is a secretive and distant planet. However, recent announcements by Neil deGrasse Tyson, a prominent astrophysicist, and Michio Kaku have brought Pluto back into the spotlight with a staggering revelation. They suggested that the world of viral content is potentially on a short course of action with Neptune. But how might this, in fact, work? Also, what may be the outcomes of such an event? Are we witnessing an awe-inspiring, limitless eccentricity, or is there another factor pushing toward a celestial incident? Join us as we examine the possible results of a Pluto-Neptune influence. Pluto, a former planet later renamed a dwarf planet, remains a topic of interest and concentration in the vast universe. As demonstrated by recent research, experts agree that Pluto's orbit is at a dangerous distance from Neptune. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about the possibility of a dangerous collision between these two planets, which could pose a huge risk to Earth. But how might Pluto's orbit even be affected by such an event? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, Pluto has only carried out one complete revolution. But interest does not stop there. Pluto's orbit is marked by its unusually elliptical shape, wandering widely from the nearly circular orbits of the major planets. What further increases Pluto's inclination is its unique orbit, tilted 17 degrees toward the ecliptic plane. Pluto moves along its path in a significantly more skewed manner than other planets. This inclination and irregularity add layers of complexity to its orbital mechanics. One of the most fascinating features of Pluto's orbit is its intersection with Neptune's. For approximately 20 years per orbit, Pluto actually has a closer proximity to the Sun than Neptune. This challenges what we would expect from their positions in the planetary system. This brings us to the natural inquiry: why has Pluto not collided with Neptune? The solution lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its initial discovery, as astronomers tried to figure out its unique route. In comparison to other planets, whose orbits lie somewhat close to the ecliptic plane, Pluto's orbit stands out with its longitude and steep inclination. As the mystery intensified, researchers realized that Pluto's orbit crosses Neptune's. However, Pluto's orbit is more stable than Neptune's. Within these complexities lies the intricacy of celestial mechanics. The three-body problem in space entails figuring out how three objects, like Pluto, Neptune, and the Sun, move and interact due to gravitational forces. It's like trying to predict their paths based on their initial positions and how they pull on each other. In Pluto's case, this problem illustrates how the Sun's gravity and Neptune's gravitational pull work together in a complex way. Several key orbital mechanics terms help explain Pluto's stability. Non-synchronous libration. In the case of Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from merging. Orbital precession. This refers to the upward movement of Pluto's orbit. When Pluto is closest to Neptune or any other huge planet, it is far above their orbital plane, offering an extra layer of protection from potential collisions. VZK oscillation. Named after three scientists, this idea describes how the gravitational interactions of Pluto, Neptune, and the Sun affect their motions. This oscillation helps us understand why Pluto's orbit near the Sun is so irregular. Despite its odd shape, this oscillation keeps Pluto moving smoothly over long periods. While space may seem chaotic, these gravitational interactions maintain balance. These factors help stabilize Pluto's orbit, ensuring it does not collide with Neptune or drift off course. Understanding this three-body problem is necessary for grasping how celestial objects shift due to gravitational forces. Mathematical simulations in the late 1980s revealed that, despite these stable properties, the orbit of Pluto is actually unstable in the long term. Minor deviations in initial conditions can lead to massive differences over time. However, for millennia, these characteristics in Pluto's orbit have maintained equilibrium over extremely long timescales. Monitoring these disruptions has been crucial. Later, automated assessments helped scientists comprehend the influence of giant planets like Neptune, Jupiter, and Saturn on Pluto's orbit. Neptune has a special relationship with Pluto. On an annual basis, for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. Jupiter's immense gravity also plays a major role in stabilizing Pluto's movement. Studies demonstrate that Jupiter's gravity is strong enough to keep Pluto on a regular path for long periods. In fact, Neptune, Jupiter, and Saturn work together to ensure Pluto's continued safe movement through space, preventing it from colliding with other celestial bodies. These gravitational forces are crucial for maintaining equilibrium throughout the solar system. Without them, planets like Pluto could collide with others or be ejected from their orbits, triggering a chain reaction with other celestial bodies. Particularly in light of discussions about a potential Pluto-Neptune collision, understanding Pluto's orbit is essential. This paints a clearer picture of the dynamic nature of our solar system. The case of Pluto demonstrates how even seemingly unstable orbits can reach a state of harmony through the intricate interplay of orbital forces and gravitational mechanics. Additionally, this highlights the importance of continuous observation and study of celestial phenomena to better understand our place in the universe. Exploring the depths of space forces us to confront the bizarre nature of celestial objects. Pluto's orbit serves as an excellent illustration of how chaos in space can still follow patterns and rules. This concept is referred to as orbital chaos, the delicate dependence of a celestial body's long-term trajectory on its initial conditions. Pluto's case clearly illustrates this. Even slight changes in its position or speed can significantly alter its long-term orbit. Using computer simulations has been incredibly helpful in figuring out how Pluto moves through space. These simulations make use of intricate mathematics to show how Pluto and other space objects, like Neptune, pull on each other. By tweaking small details in the simulations, space scientists can see how even minor changes can drastically affect Pluto's final location. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. Despite having features like non-synchronous libration and orbital precession, Pluto's orbit remains stable. Nevertheless, Pluto's orbit can still be influenced by long-term gravitational interactions. While its current trajectory appears stable, even small disturbances, such as interactions with passing celestial bodies or shifts in the Sun's gravitational influence over billions of years, could introduce variations in its path. These tiny perturbations, compounded over millennia, might eventually alter Pluto's orbit in unpredictable ways. Could Pluto ever collide with Neptune? Given what we know about orbital mechanics, a direct collision between Pluto and Neptune is highly unlikely. Their current resonance and spatial separation prevent them from coming too close. However, if an external force, such as a passing rogue planet, a significant shift in the Sun's gravitational pull, or interactions with other trans-Neptunian objects, were to disrupt this delicate balance, Pluto's orbit could shift enough to bring it into closer encounters with Neptune. If such a scenario were to unfold, one possible outcome is that Pluto could be ejected from the solar system entirely, becoming a rogue planet drifting through interstellar space. Alternatively, it might settle into a new, more stable orbit, potentially moving farther from or closer to the Sun. The gravitational influence of Jupiter, Saturn, and Neptune would all play a role in determining Pluto's fate in such an event. The bigger picture, understanding celestial stability. Studying Pluto's orbit isn't just about understanding this one dwarf planet, it also provides crucial insights into the stability of our entire solar system. The interactions between planets, moons, and other celestial bodies follow precise mathematical laws, but they are also subject to chaotic influences over long periods. This means that while the solar system appears stable now, subtle shifts could lead to dramatic changes over millions or billions of years. This concept extends beyond Pluto and Neptune. Other celestial bodies, such as the Kuiper belt objects and even planets in exoplanetary systems, experience similar gravitational interactions. By studying Pluto's motion, scientists can refine their understanding of planetary dynamics, helping us predict the long-term evolution of our solar system. Conclusion: Pluto's fate and the ongoing exploration of space. For now, Pluto remains in its unique orbit, safeguarded by gravitational resonances and the influence of larger planets. While discussions of a Pluto-Neptune collision make for intriguing speculation, the reality is that Pluto's movement is carefully orchestrated by the complex interplay of celestial mechanics. However, as we continue to explore space, new discoveries may challenge our current understanding. Future advancements in telescopic technology and space exploration missions could provide deeper insights into Pluto's past, present, and future. Whether or not its orbit remains stable indefinitely, one thing is certain: Pluto will always remain a subject of fascination in our quest to understand the mysteries of the universe. Still, Pluto's orbit can be unpredictable and irregular. If you begin with even a modest difference in Pluto's location or the speed at which it's moving, its orbit could look completely different in a matter of years. However, Pluto's chaos lasts for extremely long time scales, like billions of years. This essentially means that Pluto's journey around the Sun has a kind of order to it, even though it seems chaotic at first. ESP's ability to predict celestial events, especially when they involve unorthodox orbits as large as Pluto's, combats the inherent unpredictability of these systems. However, in the long run, forecasts are often filled with uncertainties. While mathematical models provide excellent tools for understanding and predicting the future behavior of celestial objects, they also expose the limitations of our predictive capabilities. These models heavily rely on the accuracy of initial conditions, and any small error or distortion can result in drastically different outcomes, making precise predictions a daunting task. Furthermore, the chaotic nature of planetary orbits like Pluto's reminds us of the dynamic and ever-changing nature of the universe. While we've made tremendous progress in understanding space, Pluto's case reminds us how much we still don't know. The gravitational effects of the giant planets on Pluto's orbit offer valuable insights into the broader dynamics of the solar system. They demonstrate how the presence and position of each planet can significantly affect the stability and direction of other bodies within the system. So why does this matter? Recently, astrophysicists have voiced concerns about a potential collision between Pluto and Neptune. Despite these concerns, complex forces are working to prevent such an event. Neil deGrasse Tyson, a prominent astronomer and a pivotal figure in advancing cosmology, provides unique insight into the mysteries of our solar system, specifically, the intriguing case of Pluto. Tyson's role in renaming Pluto from a planet to a dwarf planet offers insightful views on the evolving nature of celestial mechanics and the public's interest in the overlooked domains of space. His position regarding Pluto's new classification is based on an ever-increasing body of knowledge. He views the renaming not as a reduction but rather as a substantial adjustment in line with our expanding comprehension of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of constant change and learning. He uses the complexities of orbits like Pluto's as indicators of how much we have yet to discover about space. The interest in these questions continues to make space exploration so appealing. However, despite Tyson's confidence, his thoughts on Pluto's potential impact with Neptune present a different picture of his concerns. Could Pluto crash into Neptune, or is this just another moment of confusion in the ever-evolving universe? Only time and further investigation will tell. For now, we are left with a deeper curiosity about how little we still know about our own solar system. We continue to explore in the hope of uncovering more mysteries that lie beyond. The possibility of a Pluto-Neptune collision raises yet another intriguing question about the dynamics of our universe. Such an impact would challenge conventional understandings of planetary stability. The idea that two celestial bodies with such dissimilar properties could collide is both disruptive and captivating, especially when considering their current relative orbits. Pluto is situated in the outer reaches of the solar system, far from the major planets, while Neptune is a gas giant with a strong gravitational field. The implications of such a collision would be significant, offering valuable insights into gravitational interactions and the evolution of the solar system. To assess the dynamics of a possible impact, we must first consider the structure and properties of Pluto and Neptune. Despite being a dwarf planet, Pluto contains a wide range of substances and elements believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in ice made of nitrogen, and its atmosphere is primarily composed of nitrogen, methane, and carbon monoxide. Neptune, on the other hand, is a massive gas giant composed mainly of hydrogen and helium, with additional lighter elements forming a deep, thick atmosphere. A collision between such disparate bodies would radically alter their structure and behavior, potentially creating an event visible across vast distances. What makes this theoretical collision especially intriguing is the influence of other planets and objects in our solar system. While Neptune's gravitational pull plays a dominant role in maintaining Pluto's orbit, it is not the only factor at play. The presence of Jupiter, the largest planet in the solar system, is another key element. Jupiter's immense mass and powerful gravitational field provide a stabilizing effect on Pluto's orbit, preventing it from drifting into Neptune's path. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune highly unlikely. The protective dance of orbital resonance. Despite the theoretical possibility of a Pluto-Neptune collision, one crucial factor prevents such a catastrophe: orbital resonance. Pluto and Neptune are locked in a 3:2 mean motion resonance, meaning that for every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. This gravitational relationship ensures that the two bodies never come dangerously close to each other, despite their seemingly intersecting orbits. This resonance acts as a cosmic safeguard, stabilizing Pluto's orbit and preventing a collision. Even though Pluto's orbit is highly elliptical and tilted relative to the solar plane, the resonance with Neptune ensures that whenever Pluto is near Neptune's orbital path, Neptune itself is always at a safe distance. This dynamic has persisted for millions of years and will likely continue for billions more. The role of chaos in the solar system. While resonance keeps Pluto and Neptune apart, the solar system is not entirely predictable over long timescales. Small gravitational interactions with other planets, particularly Jupiter and Saturn, can introduce minor perturbations into planetary orbits. Over hundreds of millions to billions of years, these tiny changes can add up, creating chaotic behavior. However, Pluto's chaotic tendencies are mostly limited to slight variations in its orbital parameters, rather than drastic shifts that would lead to a collision. In other words, while Pluto's future orbit cannot be predicted with absolute precision over billions of years, the odds of a catastrophic event remain vanishingly low. Could an external force disrupt Pluto's orbit? One fascinating question is whether an external force, such as a passing star, an undiscovered planet, or even dark matter, could disrupt the delicate balance of Pluto's orbit and push it toward Neptune. While highly unlikely, such a scenario is not impossible. Passing stars. If a rogue star were to pass close enough to the solar system, it could perturb the orbits of distant objects in the Kuiper belt, potentially affecting Pluto's trajectory. However, such an event would require extremely specific conditions and is expected to occur only once every few million years, and even then, the effects on Pluto would likely be minimal. Planet 9 hypothesis. Some astronomers believe that an undiscovered ninth planet, lurking far beyond Neptune, may be influencing the orbits of distant objects in the Kuiper belt. If such a planet exists, its gravitational effects could subtly alter Pluto's orbit over time. Dark matter interactions. While purely theoretical, some researchers speculate that interactions with dark matter or unseen gravitational forces could influence celestial bodies in unexpected ways. However, there is no concrete evidence that dark matter plays a significant role in shaping planetary orbits. The broader implications of Pluto's orbit. The study of Pluto's orbit is more than just an exercise in celestial mechanics. It provides insights into planet formation, orbital stability, and the long-term evolution of the solar system. It also serves as a reminder of the interconnected nature of planetary systems, where even small gravitational nudges can have profound consequences over vast timescales. Furthermore, Pluto's case highlights how science constantly evolves. Just as Pluto was reclassified from a planet to a dwarf planet, future discoveries may reshape our understanding of celestial dynamics, potentially revealing new aspects of planetary motion that we have yet to comprehend. Conclusion: a cosmic balance maintained. For now, Pluto and Neptune remain locked in their cosmic dance, their resonance preventing a catastrophic encounter. While the universe is full of unpredictable events, the careful balance of gravitational forces keeps the solar system in check, at least for the foreseeable future. As astronomers continue to refine their models and gather new data, our understanding of planetary motion will only deepen. Whether through the discovery of new celestial bodies, advancements in astrophysical simulations, or unexpected cosmic events, the mysteries of the solar system will continue to captivate scientists and space enthusiasts alike. The question remains, what other hidden forces shape the fate of our solar system? Only time, and further exploration, will reveal the answers.